Hey guys, I'm Pat Kelly. Okay, in this problem, they give us an improper integral. They told us that. What they'd like us to do is to determine whether it diverges or converges. And of course, if it converges, they'd like us to know what the answer is. And if we do find that numeric answer for this integral, they'd also like us to verify using a graphing utility. So let's take it from the top. If this is an improper integral, the first thing you're going to want to do is rewrite, and we rewrite these as limits. But you have to recognize where the problem child is, what value is giving you issues. And in this case, it's the 0, because if I plug a 0 in, I'd have 0 times the natural log of 0 is actually a negative infinity, so 0 times infinity. So 0's where my problem is. So we rewrite this with a limit as b tends toward that value of 0, specifically this time from the right, because we're only between 0 and 1. And then our integral really just changes the limits of integration. We put a b in place of that 0. The 1 is still there. The x, natural log of x dx is still there. Okay, so that's the new limit problem that we got to solve. And of course, in that limit problem is still an integral problem. And I'm going to go off to the side and work on just that integral. And I'm going to work on it as an indefinite integral, just see what result we'd get. So if I had just x natural log of x dx, let's find a value or an expression for that and then take it and plug it back in and use our limits of integration, okay? So just some indefinite integral work. And even as I get rolling on this, I think this is going to be integration by parts. Okay, so let's figure out a u and a dv. U, I'm going to try natural log of x. dv would just be the x dx. So my du equals 1 over x. My v looks like x squared over 2. Let me throw my dx in here when I differentiated. And that's my pieces of the puzzle for integration by parts. So let's put those pieces in. You have to know your formula for integration by parts. You do your u and dv work so that you can then do u times v minus integral v du. It should sound familiar. So let's start with u times v. I would have x squared over 2 times the natural log of x minus the integral of v du. So now I'm looking at x squared over 2 times this 1 over x dx. That'll simplify the x's just a little bit. And I guess I would have x over 2 dx. And we'll go one step further with this scratch work just to actually evaluate that integral. It's not too bad at all. So this equals, I still have x squared over 2 natural log of x minus, bump up to the 2 power, divide by 2. So we'd be divided by 4 there, and you're done. Let's not worry about the plus c, because the point of that work is that this would be my answer for the indefinite integral, and I'll now put that in here into the definite integral that I'm working on over here. So now my next step down here is that this equals a limit still as b goes to 0 from the right. And just like as is pretty much always the case through calculus when you're working with limit problems, is you do all the work on the inside first. Algebra, calculus, whatever. That limit work won't be done until the very end of this problem. So I'm really focusing here on the integral, which I'm trying now then to capitalize on my work over here. I know that this integral ends up being x squared over 2 natural log of x minus x squared over 4, but I need to evaluate all that from b to 1, because it was a definite integral. And then I'll slap some square braces around all of that, because all of that is still inside my limit that I need to do. Okay? All right, still working inside the expression of the limit as much as I can, because I have a little bit more calculus to do. This is your fundamental theorem of calculus, right? Let's plug in the upper limit and subtract what happens when we plug in the lower limit. So this will equal limit still. B goes to 0 from the right still. Plug in that upper limit, and I'll have 1/2 times the natural log of 1. The natural log of 1 is 0. Subtract, plugging a 1 in here, I just get 1/4. We put parentheses around that, because then we would subtract what happens when you plug in the lower limit of integration. So I'll take this b and plug it in, parentheses, b squared over 2 natural log of b, subtract b squared over 4, and I'll again slap square braces around all of that because I still have to address that limit as b approaches 0 from the right, which I feel like I'm ready to do. But watch, when I get to this term right there, putting a 0 in from the right, I'm going to get 0 times infinity again. So you're still being plagued by that indeterminate form. Let me go off to the side and do a little bit more scratch work. Just addressing that indeterminate form, we need to worry about the limit as b goes to 0 from the right. I'm just worried about that one part of it, the b squared over 2 times the natural log of b. And I told you that's an indeterminate form, right? And who's the best superhero around for indeterminate forms? L'Hopital. He always comes to save the day. So let's do a rewrite. Limit still. B approaches 0 from the right still. But L'Hopital likes these expressions to be fractions, so I'll do a rewrite. I'm going to leave the natural log of b up top and shove that b to the 2 power downstairs, b to the minus 2 power. Because then L'Hopital can do his thing and differentiate top and bottom. So this equals limit still, b approaches 0 from the right still. Do your derivatives up top. Natural log of b differentiates to 1 over b. And then b to the negative 2 power, minus 2 in front, minus 4. And then b needs to drop down a power, so minus 3. And now we'll do a little bit of algebra cleanup. Let me slip down to the next line. I still have the limit as b goes to 0 from the right. And this actually cleans up algebraically kind of nicely because these 3 factors of b look like they're supposed to be upstairs. The 1 factor of b is supposed to be downstairs. So that should just leave me with 2 factors of b upstairs, right? 3 go up, 1 goes down. They simplify. B squared over minus 4 looks right. Whew. Okay, and then finally, it's an easy limit. Put your 0 in, and after all that work, you get a 0. But that work tells me over here now, let's finish this problem. I now know that that part is going to go to 0, okay, from this work here. This work here is telling me that that goes to a 0. All right, let's finish. Last line then, this overall expression equals, and I'm doing my limit, so I don't need to write that anymore, 0 minus 1/4, subtract, we just figured out that's 0, and now we're putting a 0 in for b right there, which is also 0, and so you've got your answer. All that work, and you get a nice answer of minus 1/4, okay? Good job, you pat yourself on the back, but then finally, the question said to verify or confirm with a graphing utility. So let's grab that. As I'm grabbing mine, I'll even add here how the directions did say to determine whether the integral converges or diverges. Because we got a nice answer, a finite number, it converged, okay? And that's our convergence. It goes to minus 1/4. Now I'll grab my graphing utility and my y equals from the original is x times natural log of x. Let's key that in. So not natural log of x. I'm going to graph mine. If you want, you can zoom in. I think I will on mine, depends what your settings are, but I'd like to see what's going on. All right, then when you like what you're looking at, then use those integration features of your graphing utility. Let's find the integral from a lower limit of 0, upper limit of 1. And my utility is saying negative 0.25. That's what we got, right? I'll also throw in here my graphing utility has some stray decimals after several zeros. Your utility is finding approximate answers. 0.25000 for me, 1.5, is definitely approximately minus 1/4. Our answer is exact though. So again, you pat yourself on the back. You did a good job. Okay, try some more on your own.